In this video, we're going to start looking at some ideas from finance, in particular personal finance problems that we can solve using our knowledge of exponentials and logarithms, and formulas that we can deduce from what we know about geometric series. So we're going to be looking at something called an annuity. That's a financial instrument where you make regular payments of the same size. So, for example, a loan or savings account of some kind where you're always applying the same payment every period, and the periods are regular, like every month or every year or something like that. Um, for example, if you borrow money to buy a car and you make monthly payments of $400, so every month you pay the same amount, that's an annuity. And we would call that a decreasing annuity because every time you make a payment, the balance of that loan will get smaller. You'll owe less money. On the other hand, suppose that you're saving money every month. You have $150 taken out of your paycheck and put directly into a savings account. So that would be an example of an increasing annuity. The idea is every time you make a payment, the balance goes up, it increases. And that's what we're going to be focused on in this sequence of videos, increasing annuities. The starting balance of an annuity is known as its present value, and the ending balance is known as its future value. So for example, when you take out a loan, when you pay off the loan finally, the future value will be 0. On the other hand, if you're saving money, the future value will be some positive number when you're done. Here are some abbreviations we're going to use in these videos. First of all, the future value will be FV, and later on, when we need it, present value will be PV. And we're also going to need to know the interest rate that's being used. And the simplest thing is to express it as a periodic interest rate. So if you start with an annual interest rate, you'll have to convert that to the interest rate for each period, for example, for each month if they're monthly payments. And you'll need to know the total number of payments made. One last thing that we need in these calculations is to know how much the payment is, how much money you're paying each time you make a payment. So we call that the payment size, and we abbreviate it as PMT. So for a first example, imagine you deposit $100 at the end of each month in a bank account that earns 12% interest, compounded monthly. What will the balance be after 5 years? So notice this is a little bit different than a compound interest problem we've studied earlier because you're making more than one payment. You're not just putting money in and letting it gain interest for 5 years. You're adding money every month. So the right way to think of this is first to figure out what your periodic interest rate is. And we chose 12% in this example, which is completely unrealistic in today's world. You will not find a bank account that gives you 12% interest. But it will make the numbers nice for this initial example. So we can simplify 12%, we express as a decimal, divide that by 12, and you get 0.01. That's the periodic interest rate, the amount of interest that's applied each month. Now imagine the first $100 that you put away. You put it away at the end of the first month, right? We're saving money at the end of each month. So you put that $100 away in an account that's earning compound interest. Every month it earns 1% interest. So as we saw in compound interest formulas, we need to take the amount we start with and multiply it by 1 plus the interest rate, raised to a power that represents the number of times we apply interest. Well, 5 years is the same as 60 months. Now, if you're making payments at the end of each month, that means the first payment only gets to earn interest for 59 months. So it earns interest 59 times, and this is the compound interest formula that says how much that first $100 payment will grow to after it earns interest for 59 months. Then you can imagine the second time you make a payment, that $100 you start with earns 1% interest 58 times. The third payment earns 1% interest 57 times, and so on. The very last payment you make will be at the very end of the very last month, and so it won't earn any interest at all. It'll earn interest for 0 months. And remember that 1.01 raised to the 0 is 1. So this quantity is really just 100 times 1, which is just 100, and that makes sense. That's the amount of the very last payment that goes in that never has a chance to earn interest. You put $100 in and it stays $100. Each of these terms represent how much money an earlier payment grows into by accruing interest. So now we're going to simplify this expression. We can factor out 100, which shows up in every term. And after we do that, what's left in parentheses here is a geometric sequence. These are consecutive powers of the number 1.01. 1.01 raised to the 0, and then it's not written here, but it's also raised to the 1, the 2, the 3, so on, all the way up to 59. So that's a geometric sequence, and we're adding those terms together. So we can use our formula for the sum of the geometric sequence with 1.01 for the value r and 59 for the value n. We plug that into the geometric sequence formula. Remember, this exponent is n plus 1, so that's how 59 turns into a 60 here. And this quantity you can evaluate on a calculator. Be very careful with parentheses if you do this on a calculator. Make sure you use enough parentheses in the right places. And in particular, you should probably throw in some parentheses around this entire denominator and this entire numerator when you're typing it in to make sure your calculator knows what you're trying to say. And if you do that all correctly, you should end up with a value that rounds to $8,166.97.